This is OCRN, the Organic Chemistry Reaction Network, broadcasting live with our cameraman Shane back in the middle. Let's give him a hand. My name is Tim Maris, and I'll be calling the play-by-play on the reactions today. Let's take a look at the starting lineups for today's reactions. First up, the chiral carbon. A chiral carbon has 4 different substituents. As we don't have any wires to hang someone in the air to show the proper geometry, the carbon's hat will represent the hydrogen. Next up, we have our substituents. We have Ricky, a methyl group. Ricky, come on down. Look excited. Next up, we have a deuterium. Eddie! Eddie, get out there! We also have a leaving group, Clint, who is a halogen, who will be playing the saxophone today. And our strong nucleophile will be played by Gretchen with the flute. Later on in the skit, you'll see Sochil as the small nucleophile and E1 and Priya as the extra substituent for rearrangement. We'll start off by broadcasting from the 2 world of strong nucleophiles and bases. It looks like the first reaction, the SN2, is ready to happen. Let's watch. What an amazing SN2 reaction! That happened fairly quickly, however. Let's take a look at the instant replay in slow motion and break it down. Here comes the nucleophile. It looks like she's coming in toward the carbon on a backside attack. The substituents are being pushed into a transition state as a result of the nucleophile coming closer, and the leaving group is gone! He's out of here! The nucleophile is bonded to the carbon, and we have inversion of the substituents! Next up, we'll have an E2 reaction where the nucleophile acts as a base. We just saw the SN2 reaction on that last play, but it looks like the substituents have bulked up with more atoms. We'll have to see how this affects the nucleophile strategy. Timeout on the play. Alright, and we're back, and the gameplay is underway. Here comes the nucleophile. Alright, well, let's take that one back and look at it in instant replay once again, and I'll let you all know what was going on. He's coming in toward the molecule. Oh, and she is denied by steric hindrance, one of the secrets of OChem. Oh, denied again, that's gotta hurt. But she doesn't look like the kind of molecule to be going away empty-handed. She just stole a proton from one of the substituents and has become positively charged. A double bond has formed and the leaving group is again taking off in a concerted fashion. But this time it looks like the leaving group, which is negative, is going to hook up with the base. What a great way to show that in E2 reactions, nucleophiles act as strong bases. That, ladies and gentlemen, is a textbook E2 reaction. But the double bond didn't have to form on only one substituent. It could have happened on the other side instead. Let's take a look at a not-so-instant replay to demonstrate the regiochemistry of this reaction. The base is coming in. She is again denied access to the carbon. Ugh, again. That's gotta hurt. But this time she grabs a proton from the other substituent. A double bond is forming on the other side, and the negatively charged leaving group is again taking off with the base. That's what we in the biz like to call regiochemistry, which refers to the different orientations in which double bonds can form. Well, that's all for the 2 world. We're back for another reaction, but this time we're entering the 1 world of weak nucleophiles, where the nucleophile does almost nothing. Just a reminder that these reactions are brought to you by the University of Minnesota, enriching minds and lives. Alright, the SN1 reaction. Here, the nucleophile does almost nothing. The nucleophile, she's circling around, but before she does anything, the leaving group takes off. Astonishing! And now the substituents are planar with the carbon, but not for long. The nucleophile is forming a bond with the carbon on the back side. Now the substituents resume their tetrahedral position. What a great SN1 reaction! But that reaction doesn't always have to happen that way. When the substituents are planar, the nucleophile can attach on either side of the molecule. Let's take another look at this reaction. Here comes the nucleophile. She's coming in. Nothing's happening. The leaving group is gone. The molecule becomes planar. And the nucleophile attaches on the front side right where the leaving group was. What an amazing SN1 reaction. Thus we can see that no matter how things line up in an SN1 reaction, we'll always get a 50-50 racemic mixture of the 2 possible products because each form is equally likely. But this reaction could have gone yet another way. Yes, it could have been an E1 reaction. In this reaction, the nucleophile is really slow. Are we set? Too many men on the field. Okay, in this reaction, the nucleophile is really slow. Here, the leaving group again takes off before the nucleophile is even close. And this time, the leaving group is taking a proton from one of the substituents and getting out of there. But the nucleophile just isn't in the game at this point. So the substituent who lost a proton forms a double bond with the carbon, leaving the nucleophile out in the cold. And it looks like that leaving group that left with a proton has become an acid. Boy howdy, that's an E1 reaction if I ever saw one. And now it's time for my personal favorite, rearrangement. What you will not find in the 2 world, because rearrangement only happens in the 1 world. In this reaction, we have an extra substituent bonded on. The nucleophile forms a bond with a molecule other than the expected carbon that had the leaving group in this one. Let's watch the fun begin. The leaving group takes off from the carbon, leaving it with a positive charge, making it a lousy carbonium ion. In response, the carbon grabs a proton from one of its neighboring substituents. Now the nucleophile can't form a bond with the carbon, so she comes over to the substituent that just lost its proton and forms a bond. Yes, that's right, the nucleophile formed a bond with a molecule other than the carbon from which the leaving group was attached. That is rearrangement, ladies and gentlemen. Well, all the atoms took part in some pretty amazing reactions today. Boy, reactions like those, they really make organic chemistry look good. Well, that's all for this broadcast. Until next time, I'm Tim Maris for OCRN News, signing off.